Brave tab. So do you see this one?
No.
No, not yet. Yes, it's
I
coming.
see something. Yeah.
Okay, so this is the homepage of the project. Start with the HomAlg is just the historical name. Now HomAlg is harboring many projects. So it's harboring the CAP project, the HomAlg project, the so-called higher homological algebra, and the toric varieties, and we are splitting these projects to be manageable. Yeah, and the name is just the historical name. And one of the big projects that we are now working on is this CAP project. The CAP is an acronym for Categories, Algorithms, and Presentation. And historically, this is coming from the fact that homological algebra really needs a lot of category theory. This is basically the PhD thesis of one of my two PhD students, Sebastian Gotcha and Sebastian Pozo. And now I will go on CAP-based projects. And here is the concept of categorical doctrines. And if you scroll a bit, then you will get to the categorical constructors at some point. You see here?
Mm-hmm.
So category constructors and building towers of categories. The CAP-based packages provide various category constructors which take a combinatorial or algebraic data structure, or even a category or several categories of a certain doctrine as input, and provide another category of a possibly different doctrine as output. The true strength of CAP is that it allows concatenating these category constructors to build arbitrary high towers. Of course, the ability to build arbitrary high towers comes from the fact that you have all the time the same categorical interface. So we don't need to invent interfaces in computer algebra anymore. We simply take the well-defined interfaces of category theory, and we now understand them as algorithmic interfaces. Yeah. If you go above, you will see how such an algorithmic interface looks like. So for example, the type specification of a kernel, for us, we understand the notion of a kernel as a category theoretic notion. And to talk about a kernel in category theory, you need what is called the kernel object. So you see here, the specification of a kernel is much more than just, it's the set of all elements such that, because in category theory, there are actually no elements. You're talking about the kernel object and the kernel embedding and the so-called kernel lift. And all of these, if you click here, you go more or less to the documentation. Mm-hmm. See, so here is the specification of what is a kernel in category theory, and here is the specification of the ingredients of a kernel. Yeah. Mm-hmm. So you see, this is something you can ignore. You can look at this: the category object, the category embedding, and the kernel lift. I'm sorry, the kernel object, the kernel embedding, and the kernel lift, and you reach them from here, if you want to have a. Exactly. So let's go to this category constructors. And you see here, these are the categories from scratch, where you actually have nothing else and build them from scratch. Among them is this very trivial category. It's called the terminal category. It has just one object and one morphism, which is the identity morphism. And then something we built from scratch is the category of finite sets, also the category of skeletal finite sets, because we need this for very many basic computations. Mm-hmm. The category of skeletal fin G sets, finite G sets where G is a group, but also the category of fin G sets, but this is not official yet. You also can take a group in GAP and view it as a category. You can take a ring in GAP and view it as a pre-additive category. So this could be called ring as pre-additive category. You can take a path algebra and view it as an algebroid. So an algebroid is simply a pre-additive category on objects, on finitely many objects. This is the representation category of a finite group, and so on. The matrix category is the category. I think it requires a field. Yeah, so you give it a field and you view the set of all rectangular matrices over this field or skew field as a category. So we don't talk about matrices, we talk about morphisms in the matrix category. This is the generalization to unital rings. Here we have graded left presentations and so on. And now you have constructors that take categories and produce categories. So this is from nothing, produce a category, and this is at least from one category and produce another. So of course, this is the textbook, the first textbook construction, the opposite category, the product category A cross B, so that your objects are pairs and your morphisms are pairs. The linear closure, the twisted linear closure, the additive closure. So here, if you, for example, take the ring, view the ring using this construction here, ring as, where it is, ring as category, yeah, and then you say additive closure, then you will end up having this category of rows. So you see here, some of these constructors can be split into two. So this guy is the concatenation of ring as category together with category of rows. Yeah. And you have a lot more. You have the Serre quotient. This is the guy that I introduced during the talk. This is the one which gives me the modeling of coherent sheaves. This is the one that is can be used to construct free abelian categories. Yeah. I also have the functor category. So I will show you this today if you're interested. This is the solution of the exercise. You have a category A, and you have a finite diagram category. Then the functors from the finite diagram category into your category is again a category, and it has all the doctrines of the target category. So if your target category is additive, your functor category is additive. If your target category is abelian, or functor category is abelian. So this guy even takes two categories as input. It takes an algebroid as the first argument, and it takes an abelian or additive category as a second argument. And I think at the moment, the implementation is only limited to abelian in the target. So you take a finite dimensional K algebroid as the source and a K linear abelian category in the target, and so on and so on. So this is another stuff, and here construction of full subcategories and subcategories. And you see this is actually what we're doing now. We're more or less creating constructors. This is something I'll also maybe show you today if you're interested. You can also make the concept of laziness also as a category constructor, so that you have a layer in which you simply gather the commands you want to execute, but you really don't execute them. And maybe on this you can do logic instead of doing computation. So first you do the logic, and when you have exhausted the logic, then you can start the down-to-earth computations. So let me choose one of them and show you how this works. Yes, so let's look at this Serre quotient. No, actually there is this generalized morphism. This is this one.
Yeah.
This is one of my favorite categories. So what does this do? It takes from you an abelian category and construct the category of generalized morphisms. So this is an embedding of the abelian category in another category in which you can invert every morphism formally. And
you have to explain because you introduced this concept, Mohamed. So.
Yes, actually it was there before I introduced it. I introduced it under this name, generalized morphism, but it was there since the 70s. We figured out it was under the name linear relation categories. So instead of looking at generalized morphisms, there is a lemma due to Gaussat, actually, a very old lemma that tells you that you can view linear incidences between two objects as a sort of generalization of a graph of a function. Yeah, and this is the same concept. So we're replacing morphisms by linear relation between objects. And when you have a relation, you know that the relation always have an inverse, because you can simply switch the arguments, yeah, in the relation. And the diagram chase is nothing but embedding the abelian category in this generalized morphism category, or this category of linear relation. In this category, you can view every morphism as a linear relation, so you can compose and invert. In other words, you can invert every morphism formally. So when you're doing a diagram chase and you have one morphism which goes in the wrong direction, you can simply invert it and compose. And all the diagram chasing theorems or propositions or lemmas tell you that the composition of this composed with the formal inverse of this, composed with this, with the formal inverse of this, and so on. At the end, this end composition will end up being, again, a morphism in the abelian category, which is embedded. Yeah? And this is, of course, makes programming very easy. Let me show you how this is, how something like this is. This is by, let's look at cospans. And let me now stop sharing this. And I share my terminal. Do you see this guy now?
Not yet.
Yeah,
It's coming.
it's coming.
Okay.
So I'm now going into the cat project. And then I go into generalized morphisms. And here you can say, you see generalized morphism by spans. And actually, I can do even better. Instead of going to the terminal, I can go to the web browser. So you can see that everything is online. So let me again disconnect this and go to the Brave again, share. So you see here, I can click here again.
Wait a minute.
Wait. Yeah.
Okay, it's loading, slowly loading, and
Mohamed, maybe you could say, or you can install it, HomAlg, everything, right? It's not, maybe you can say, or you can install everything.
Yes, I will.
Because this is really simple now, and I think.
Yeah, I will. So do you see the screen?
yeah.
Yeah.
So I will go now to generalized morphism by cospans, right here. You see, this is this package, and then you go to gap, and then you click on, so here you find the documentation, but inside gap, and of course there is a manual. You get the manual either online by going here and pressing on the HTML or the PDF manual.
Okay.
Yeah, I'm now in this package. It's inside the CAP project, generalized morphism. So this is what I got when I clicked here. Mm-hmm. Once I click here, I end up there. Actually, we should end up on the README and not there. So you see this. You can go up, go inside the code, and see how it looks like. This is the generalized morphism by 3 arrows. This is what I was talking about during my talk. You remember I had these two rectangles, and I was constructing a big rectangle. Mm-hmm. And here, so let's see how the pre-compose, for example, work. Yeah, so I'm having, the idea is that I'm having, do you see me? Yes. Do you see my picture or just my screen?
The screen.
I don't have my video on. No. Start sharing. Okay. So the idea is now that you have a generalized morphism is a 2-leg like this. It's a cospan. This is a span actually. And you have another span. And what you do is you take the pullback of these two. So you get something on top, and then you compose this one and this one. Yeah, this is how you compose. So instead of the composition of these 2 legs is this bigger leg. Yeah, and let me think. This is called a cospan. No, this is called a span because so I have to go back here. So let me see how the composition of spans work. So pre-compose. Yeah. So fiber product is the name of what is called the pullback. So you see here what's going on. The pullback diagram, I'm taking the arrow So the forward arrow of the first morphism and the reversed arrow of the second morphism. These are the adjacent legs. And I'm taking the projection left and the projection right. These are the legs above. Yeah. So the projection in factor of first fiber product, comma 1. I'm taking the first one and then the second one. Yeah. And then I'm pre-composing the leftmost legs and composing the rightmost legs, the one that I didn't already use. And you see how the code looks like. So I'm taking now a these are morphisms in the underlying category. These are morphisms in the underlying category. So you see here, I'm breaking the data structure. I'm getting in with two morphism in the generalized morphism category. I'm getting the one ingredient of the first morphism, another ingredient of the second morphism lying in the underlying abelian category. And then I'm doing operation in the underlying abelian category on this diagram. And then I'm composing in the underlying abelian category, this, and this. And then I'm viewing this again as a generalized morphism. So this is how the code looks like. Yeah, and this is the code which is responsible for any diagram chase we are doing.
Okay.
Yeah, and it's more or less textbook.
Yeah.
If you understand the theory, it's the textbook. And the one that I was introducing or describing in my talk, of which you have, is this 3-arrow one. So the pre-compose is, so I used, yes, I used this here. So more 1 and more 2, I think I used, yeah, I think I used this one here. So this is the general case. And this is exactly the slide that I showed you. So let me package HomAlg Talks Paris. Paris PDF. I'm scrolling to the point. So I'll stop here. I'll share this one. Share. Now, application window, this one. Yes, so this is the left morphism, this is the right morphism, and this is the 3-arrow description. So the morphism, this is the one living in the generalized morphism category by 3 arrows. And it consists of this data: an arrow in the underlying category, which must be a mono, an arrow in the underlying category, which is arbitrary, a category in the underlying category, which must be an AP. Yeah. We're not talking about injective and surjective. We're talking category theory, mono and AP, yeah? And they don't even need to correspond to sets or anything, yeah? Okay, and the second one is the same, and what was implemented there is this algorithm, yeah? So you take this composition here, of course you bypass the identity because this is irrelevant. So you get the alpha, and then you take the image co-image or simply the image because these two are the same. You take here the pullback, you take here the push out, and then you have to invert this guy. Yeah? Okay, so, and more or less this is what is there. The only thing is that we can identify these two just in one object. Yeah, so you don't see the inversion of this. I just do this for didactic purposes so that you see that you are using all the axioms of an abelian category. Yeah? Yes. This is the inversion of this guy is what distinguishes a pre-abelian from an abelian category. Yeah, and if you could have this in mind, so what are we using? We're using composition to get the alpha. We're using images we're using pullbacks and push-outs. The pullbacks are called in cap fiber product. So if I stop this and go then back to the Brave window. So you must see here a pre-composition. You must be projection of.
Yeah,
it's
still loading. Okay, it's good.
Yeah, you see it's a pre-composition, projection, blah, and you must, here you see the push out. So here you see the pullback, here you see the push out. Yeah, and this is exactly the diagram I was showing you. So this is the general case, and as you see here, we even have degenerate cases. Yeah, so for example, if the first morphism has identity as range and blah, then just do this simplified algorithm. So you see that we've also implemented special cases in this way that also CAP is supporting, and this is the fallback. This is the full-fledged guy that I was presenting. And this is valid under no conditions. So every one of them is valid. All these shortcuts are valid under some conditions, and this is the generic guy.
Okay, so it's pretty much expressing the diagram.
Expressing, what you would do diagrammatically or on paper. Yeah. You see?
Yeah, I see.
And just before I go to the installation, I want to show you how this functor category works. And it's basically the solution of this exercise. Given a category, I don't know, D for diagram and a category A, show that every limit in A is existing in the functor category from D to A. So the functor category has all the limits of the target. If you have co-kernels in the target, then you have co-kernels in the functor category. If you have kernels, then you have kernels, and so on. If you have direct sums, then you have direct sums, etc., etc. So I'll go back there, and then I'll go to Home. So I'll click myself back until I go to the categories from categories, and then I look at the functor category, and then I can jump there. Once I jump there, actually I should jump to the README and not to the code. We will fix this. And here you can look at the documentation, or you can directly go to the code, and you see here there's something called functor categories. And this is the solution to the exercise that limits in the target category are existing in the functor category. And you see here, if you know the place, that I'm now writing functions. It's called, where is it? This is functoriality, return. It's a long time ago, so yeah, for example here, a constructor for your universal objects, for example, kernel object, yeah? So now I want to construct the functor category, and the objects in the functor categories, are functors, and the morphisms are natural transformations, yeah? Okay, and this means when I want to construct a limit object, the limiting object has to be a functor. Yeah, and you see here I'm constructing the object function of the constructing the morphism function of the functor. The functor has two functions, one which acts on objects and one which acts on morphisms. And here that I'm unpacking the functor, so I'm applying the functor on all the objects I have in the source category, which has finite, is exactly this exercise. Yeah, more abstract, because I want to exercise any limit I have in the target, I will have in the functor category, and this is the implementation. Yeah, I have here a certain limit, and the name of the limit is it's passed through the oper. The oper could be kernel object. And through the kernel object, I want to pass it so that my functor cat kernel objects. Yeah, and of course this is more elaborate than just the translation one-to-one, like in the previous one. In the previous one, I told you I want to do the pre-compose, and I know how to do it by using a finite amount of operations from the other one. But this thing here is parametric. Whenever you have any limit in the underlying category, in the range category or the target category, I can get the same limit in the functor category. And this is how complicated the code could look like. Yeah. So this is the other extreme. How complicated a step in the tower could look like.
Okay.
Yeah. And now we can go to the installation. Should be actually fairly easy. You click on this, and you see that depending on you need some prerequisites. So if you have Linux, then you need at least these packages here. And Linux means for us just Ubuntu in a more advanced. Everything else is adaptable. So you can look exactly at what we want to install and more or less do the same. Yeah. And for Windows, you have to use the Windows subsystem for Linux and more or less go again for the Ubuntu solution or whatever Linux solution you prefer. The only thing is that we need these packages. We need curl, wget, and git. And we need some installation of Julia on your system. This is more or less the standard one, but you can, of course, install your own Julia. This is just for the default user. If you can get the Julia functioning on your laptop, then everything is fine. Yeah, and then you're inside Julia and click on this installation instruction for cap and HomAlg. And these are exactly the two commands you need.
Yeah, simple.
Okay.
Then you can use a notebook.
And afterwards, after you have this, you can use the notebook. For this, you need to get iJulia. I think this is described here on the main page. So if you go to Jupyter Notebooks, there, you can clone the repository containing these notebooks here. The notebooks require Julia packages and HomAlg. So you need to install iJulia. Yeah, so you add Julia and then using iJulia, and then you start a notebook. And inside the notebook, you can say using cap and HomAlg. So it should in theory be fairly easy. And Alban, I think, went through this exercise at an early stage and then at a later stage where things have stabilized.
Yeah, now it's really simple to install everything. Yeah, so yeah. Mohamed, I don't cap now. For what you add in HomAlg, meaning put some theorems and do some inference.
Yeah. So
that
what was HomAlg was some kind of dream. We wanted to realize modules on the computer, and modules for me meant that I want really something intrinsic. If I think of a module, I want to think about the module in all its generators representation or representation pairs. So I want all the pairs of generators and relations, and I can without really changing the object. So this is what I called intrinsic. Some sort of laziness when I ask a question, compute, but it starts thinking. I wanted to put theorems inside. It can exploit all the positions and lemmas and theorems we know about in the literature. And I ended up creating this HomAlg project, which realizes all this concept of laziness, of learning objects, of logic, of intrinsic, of all this in just one layer. eventually, at some moment, I got stuck because I was not able to do the same again for, it was a lot of work to do it again for graded modules, even more work to do it for sheaves. Yeah. And at that point, I figured out that we really need something more. And I was trying to impose the same ideas on my student when they started constructing or thinking about. Thing was that they were not owned by all these ideas. Yeah, pushing. I was pushing for patching. I was pushing for laziness and so on.
Yes,
the connection is bad.
Is it better now?
Yeah. There's some lag.
You have some.
Now?
You have a bit of lag. Sometimes we miss some words. Sometimes.
Okay. Sure. I will.
Il a fait, enfin, ça fait des années qu'il développe ça. Étudiant. Et moi, je trouve que c'est un des trucs les plus impressionnants de calcul formel par rapport aux maths, quoi. Et là, ce qu'on voit pas, c'est que ça calcule, en fait. Il s'intéresse à la construction, mais derrière, ça calcule, quoi.
Are you hearing us?
Ok.
Still, we can't hear you. You haven't connected to sound to your mic. Yeah.
Can you speak?
Not yet.
Can you hear me?
Yeah.
Yeah.
Okay. So somehow I realized most of my dreams in this module package of HomAlg, and multi-layered. So it has something which is abstract, just homological algebra in abelian category, and it has this interfaces to the multiple computer algebra systems, and to Singular and to Magma, and use this transparently as if they're one computer algebra system with the same commands.
Can you show the slide of describe can you show the slide of HomAlg where you describe the connection? Yeah, for me, it's clear, but I don't know if it's clear for Antonin.
So here you can go to this HomAlg base, from there to the HomAlg project, and there you find the slideshow, probably looking at. And let me just go to the last slide. So HomAlg is implemented in GAP.
Can you make it a bit bigger?
Bigger, of course.
Okay, nice.
Yeah. So HomAlg is implemented in GAP, and these are the three categories I'm interested in. I was interested in the category of modules, of graded modules, and of sheaves. Yeah. And I need for graded modules, I need graded rings. For modules, I need all sorts of rings and so on. And here I have the interfaces to the oracles on this green layer. So the warmer the color, the more the computation. So these are the working horses, or the so-called Grosvenor bases or Gauss engine. At the bottom, they're doing the heavy lift, all the computations. The green are the interfaces. You see that we have an I/O interface that can connect us to all these systems, but also dedicated interface. We used to have a Maple for HomAlg, which is communicate with Maple via the C interface. Is on the lowest level. We had here another package called the Singular interface. Is not working anymore, but we now have substituted it by Julia. So now we can communicate with Singular via Julia directly. And how the old structure, and you see here that I was basing graded modules on, basing sheaves on modules, and this was somehow where I got stuck. This package wasn't as good as this one. And this package is the starting point of CAP. because at that point, a lot of concepts were basically in this modules package. Some stuff was outsourced to HomAlg. So this is the abelian category setup, but actually it was flexible. It was just an abstract abelian category, but I didn't to build the towers. You know, it was abstract, but it was not as clean as in CAP. And when I suffered a bit to get this modeled on that, and when I did this was really the explosion of complexity. When the Sebastians started their PhD, started explaining them all these ideas, and they had a really when I was pressing them to do all these concepts simultaneously, sometimes my pressure was strong enough, but sometimes they could resist my pressure and tell me that this is actually another layer. And now we have different layers that actually can be different layers of this HomAlg philosophy that are now clear that they are clearly distinguishable layers in CAP. The laziness, the logic, the caching, the intrinsicity or intrinsicness of the object, so that you can have different representation under one object. Yeah. What did I say? The laziness, the logic, the caching, being intrinsic. Things like having generators. You know, when you talk about objects in a category, there are no sets. But if you want to again model them on sets, when you work with modules, you want to think about real generators, and you want to, if you have application and topology, you want really to think about what is the co-cycle. I now have the homology, but really give me now a representative of the co-cycle. And all these concepts I was able to remodel a posteriori using CAP using different layers of CAP. Okay. Yeah. And now things were unbounded, you know? So I wasn't stuck anymore. They really managed to help me get rid of being stuck somewhere, because all the concepts are very clear and very separated now.
So can you, is there somewhere where you can show that you put theorems like a Grant-Suslin theorem, or this layer is no more available?
No. I mean, what you can do, you can do things like you can compose two morphisms, two monos, and it tells you the composition is a mono without any computation. This is part of it. And let me show you all the theorems that are in CAP. There are more theorems in HomAlg.
Oh, we lost Mohammed.
Sorry, I was. This was the wrong.
Misclick.
I'm sorry. This was the wrong tab. This was the wrong tab. I'm sorry.
So do the object can learn during a computation, Mohammed, still?
Yes, they can learn. We also have something even better than before. They can also learn a posteriori. So I don't know why the camera is not working. So let me try it again.
The camera was working. It was working.
Was fine. Working, but yeah. I didn't see it here on my.
Oh, strange.
Okay.
Okay, now we see you at least.
Okay, you see me. I don't see me, but it's okay. So I can show you the theorems that are in CAP. These are the theorems just on the categorical level. The theorems on the module level are still in HomAlg.
Okay.
And this is why I am now able to create categories, CAP categories, that are managed both by HomAlg and by CAP. Mm-hmm. So I can have my theorems from HomAlg, and I have the multi-layering and the correctness from CAP. Okay. So let me show you first of all the theorems in CAP, and here I do go back. Yes. So no, you don't see anything because I didn't share my screen. So I'm back there.
So in the new implementation, object can learn from themselves still.
Yeah, still, yeah. And so do you see my screen?
Yeah.
So now we can go to cap again. And now you see here logic for categories. So you see what I did? I just clicked on cap.
We see.
And then you click on logic for categories.
Mm-hmm.
But this is now the logic of the doctrines. You don't see a module here.
Mm-hmm.
Yeah. And you can see what is, I don't know, proposition for general categories. This wouldn't be much. And then this is LaTeX code, and it's taking the LaTeX code and producing a more a computer code out of it. So this is telling me the identity is an idempotent. The identity is 1 in the category, and some trivial stuff. The kernel embedding is always a mono. The co-kernel projection is always an AP. The embedding of equalizer is always a mono. The projection onto the equalizer is an AP, and so on. So once you do this computation, you don't want to, and there must be something with pre-compose.
So it's your list of theorems, okay.
Pre-compose. No, I don't see it here.
Yes, it is.
Yeah, here, yeah. So this is the composition of 2 monos is again a mono. Yeah. And the nice thing is this stuff, you see it as LaTeX as part of the manual, and it is the same code that really creates the theorem inside CAP and installs the method. So this code has a double function. It documents the theorem in the manual, and it installs the theorem in the system.
Okay. And you can update, if you update this file, it will update
every installation.
You change something, you try something, you remove one axiom, one theorem, and you see what.
Yeah, if you remove, so let me show you at least the positive effect. So the problem is if I remove one, it can be deduced by other things. So a lot of stuff here is redundant.
Yeah.
You know, because it really also depends. This is the theorems for any category. But if I do something now, it will be in abelian category, and he will deduce it probably from somewhere else because I'm now higher in the doctrine.
And can you trace this so that you can have a theorem or an exercise?
Yes, you can trace this inside. You can ask for the so-called logical to-do lists that he triggered. And you have them in the cache, and you can see exactly what he managed. And with every object, and this is better than HomAlg, this was actually the end of the logic in HomAlg. We introduced so-called a priori logic, a posteriori logic. So you are computing on one object, and there the computation is actually an increase of information, right? Every computation is an increase of information. And then you go and compute somewhere else. And what is new now is that all objects are connected. So if you acquire knowledge about a related object, this will fire back. You see? So for example, if you have a sub-object of another object, and then you figure out that the super object is, I don't know, simple, then you know that this guy here, the one, is either 0 or isomorphic. And then you know that this guy is not 0, so you know, it's isomorphic. I can carry all the information I acquired about the super object back to the simple object, and I can update my information of this guy as being ISO of the connecting one, of the embedding of the sub-object as being ISO. And then another morphism, which is created as the composition of this guy and a mono, knows, this is not just an abstract morphism, but also an ISO, so it's a mono. So this whole thing is a mono. And then you start, so the another object, the final target now has a simple object in it, so it's not 0, you know? And this firing starts. And I was also eager to do this in one layer, and it is actually still in one layer. But what we will do is that we will disable this and enable it on demand. Because we now know that there are a lot of very basic categories where this is a huge overhead. You don't want to do this on the bottom, on the very bottom.
Yeah.
I was wondering of that. It seems like a lot of information to carry on and spread.
Yeah.
And
yes, and of course I was coming from where Alban is coming from. I'm coming from Grosvenor bases. And there it simply means anything you can do to avoid any computation is a win.
yeah.
Yeah.
Because the alternative could be computing a Grosvenor basis.
Mm-hmm.
Yeah. So, and more or less this stuff is O of 1, you know? It does not really depend on the complexity of the input.
Yeah.
It just depends on the number of objects you have already computed, not on their size. So it's an O of 1, it's a constant factor. And when you are competing against double exponential complexity, then O of 1 is always negligible. But of course, when CAP became so flexible, we were also creating so-called working horse categories like fin sets, and with a lot of very simple operations where you actually don't want to invoke logic anymore, because these operations are then linear or even polynomial or even linear time. So you don't want logic on this level. But the nice thing is that somehow they had this also in mind, and this layer is easily, so it can easily be put off and triggered on demand.
Yeah, I don't know if you can show again, when you do a computation, the time of thinking and the time using theorems and thinking and the time of computing. It was very impressive in HomAlg that it can trace when the system is thinking, not computing, applying theorems, etc., and the time that I was computing.
So I think what you showed was just the logic of on the level of matrices. Yeah. So let me show you this. We did not incorporate this on the higher stuff. We can do this, of course, later at some later point when we have some better graphical interfaces. But at the moment, I'll do a computation. This is maybe the computation that I also showed you, the one which is computing which is solving the
spectral sequence,
PDE.
Yeah. It's really impressive to see the time that the system thinks in respect to the.
But this is now definitely not the full-fledged one. So
this
is just the level of logic on the matrices. And actually, this is already HomAlg. This is not CAP anymore.
Yeah.
So let me share this. Okay. Software, I think. So this was this PDE system, linear PDE system over the Weil algebra. And I wanted to simplify this system using spectral sequences. To do spectral sequences, I would then use the diagram chase using the generalized morphism that I showed you before at the beginning of today's informal session. And what I will do here, maybe this will, I have to be aware because I'm playing with the system. So I hope this works. And before that, I'm opening the debugging. So now you see the communication between gap and singular. And everything which is blue is something that the system thought and stopped the computation before passing it to singular. And everything which is red or green or something, this means it went through. So filtered on purity by purity. Okay. You see the blue here is trivial computations that he could avoid. Yeah. You see that he figured out that somehow the higher logic wants that this operations on the matrices are passed to the system. Yeah, a one matrix times an empty matrix. Yeah. So this is the trivial stuff, and a one matrix times another matrix. So this is some 4x2 matrix, but it should be multiplied with a 4x4 identity matrix. Yeah, and you see some computations done, but then again, the system is asking the oracle to multiply a matrix with a 1x1 matrix. So, and of course, this is also a categorical logic. This is as if you're in a category and you're composing a morphism with the identity morphism. Yeah. So this is the precursor of the logic in CAP. And you see here how many logic was, sometimes it computes, but other times it finds out a lot of logic. And see here? And it stops computing.
Okay.
Yeah. And definitely, so you see here, let me do this again, but now without. So n is this, and by just this computation, no, not by this, but sorry, filtered by purity, you see this computation triggered in the background stuff so that, actually we'll see here a lot of things. I'm starting with this object n, and you see I'm not assigning it, so it's computing something, and actually what I got is a side effect on n. And you see here, n was on 8 relation for 2 generators. The same object now is now internally represented in another way. It's represented on 3 generators for 6 relation. And in the meanwhile, it knows that it's a non-pure module. And it has what Alban, I think, also calls the grade, right? Grade 1, although this was not explicitly part of the computation, it was deduced during the computation.
You learned something during the computation.
And now even you can say on original presentation of n, and it jumps back to the ugly one, but it doesn't forget the
information.
The information. Yeah, and you can jump forward again.
Yes.
And the nice thing with CAP is that this level, which now works for modules, works for any category, any. Yeah, I can do this intrinsic business on any category. I just need to define a CAP category and so-called auto-equivalences. These are functors that give me an auto-equivalence on the category, and then I tell a package called intrinsic category, take this category, take these auto-equivalences, 1, 2, 3, 4, up till 200, and make all of these functors into the identity functor. Meaning, if I apply them to the object, put another object internally, link it with the natural isomorphism to the identity that is part of the data that I give you, and manage all of these objects in this big hull so that I can change between all of them. And this is how I was able to do HomAlg again using CAP, but in different layers.
Yeah.
Okay. It's very impressive.
Can you say a bit something about the compiler? You say that you want to scratch down everything from all this computation.
So first of all, let me show you how I will tell you something on the compiler, but on this example, yeah?
Okay.
So I want to now go to package intrinsic modules. Git checkout. Maybe this is not, no, this is not tested, but maybe just let me show you. I will not compute here, otherwise I'll run into an error, because this is exactly what I'm altering now. So autogap and procedure. Actually, this is a good one, so I can show you this. But I have to disable the error message that I have inflicted. Categories, and object git diff, yes, git stash. So I have to start this again. So I'm loading a package called intrinsic modules. This is the redoing of the modules package inside CAP. And you see now that I need a lot of packages. Yeah? I even need the generalized morphisms to do the generators. I'm now modeling the generator using the generalized morphisms. I'm not even doing snake. or any diagram chasing, but the very idea of an element of a module, we figured out that for this we also need generalized morphisms. Yeah. And now I load this package. Also, this is probably and here you see I'm creating the ring of integers in an external gap. So I can even use not the gap I'm working in, but I can even use an external gap. And this is the presentation matrix. So the ring is Z, so it's very simple. And so actually let me stay here and make the copying from there.
And then torsion left module.
Yeah.
So you already learned something.
Now, intrinsic modules. So let me copy from here. So now
so the fact that it is left non-torsion, the system has
detected from I have 3 generators and 2 relations.
Yeah,
so
okay.
it's
but there is a procedure to learn that from
exactly.
Okay.
Exactly. And now I'm computing the endomorphisms of and so here I'm computing the endomorphisms.
Yeah.
Okay.
So as a module or as a
module. So it's a non-torsion right module. Yeah. Of course, everything is commutative, so you can ignore left and right. Yeah.
Yes.
And you can even, out of this one, compute its own endomorphism ring.
Yeah.
And then you can say, I want to, so this has now 20 generators.
You can display it just to show.
So display E.
Just to see that it computes something.
Yeah, so this is the presentation of the module, but now I can tell him buy a smaller presentation on E. Yeah. So this is an abelian group, a Z module, yeah? If I say buy a smaller presentation, then it's just on 7 generators given by 6 relations, and if I display it again, I see
what happens in the background. It's a Gauss reduction or
Smith normal form.
Yeah, okay.
Yeah, and now you see the abelian invariance.
Yeah, the invariant factors.
Okay, and now I can get the generators.
So you know the rank is 2.
Yeah. The rank is 1.
Oh yes, 1 by 10 was 1. Yes. Yes.
So now I have the generators, and what is E? E was the endomorphism of N, and N was the endomorphism of M. Remember? Yeah. And now I can perform the on G, the display, so I can show you all the morphisms. These are these guys. Yeah. So these are these 5 by 5 matrices with the big numbers.
Yeah.
And then I can say, okay, now these are what? What are these numbers? These numbers are, what are these matrices? These are the endomorphism of the module N.
Yeah.
Yeah. You see, E was the end of N. So now if I go and say buy a smaller presentation of N, now N again gets in normal form by the Smith. And now I can say, okay, please show me the generators again. These are the generators of the endos. And now they are 3 by 3, and not 5 by 5. This is, and now you can even do more. You can say, and now please take into account the relations of the target module, and then show them to me again.
And the update of these presentations is
lazy.
Is lazy. It's when you ask to display.
Yeah.
Then it performs.
It's lazy. This is also one of the nice concepts you would like to have, but where I faced a lot of resistance from the Sebastians, and they were right. And I ended up really having my own lazy category. So you can say lazy category.
Okay.
Yeah, so I didn't use it here because I'm now using the laziness of HomAlg. As I told you, now HomAlg is managing this CAP category. So it's managed by CAP and by HomAlg. And it has the laziness of HomAlg as well in it. But there is something where you can make every operation lazy, every operation. And then you can display the graph. When you say I want to compute the snake, then you can really see what this will trigger in the background before even computing the snake.
Yeah.
Do you have any project now on group theory or topology, algebraic topology?
So we have several projects. So let me think them in order. So first of all, the compiler. We have to come to this.
Yes, right.
Okay. So we branch from the compiler. Yeah. So I have now the idea of making Grosvenor bases equivariant.
Yeah, you told me. You told us, yes.
Yeah, this has of course to do with group theory or with reductive group theory or with semi-simple Lie algebras or whatever you want to say. So yeah, this has to do with all this.
But this is a mathematical problem. There is no solution. It's not just a problem of.
No, it's a mathematical problem. We have to get. So we have now the data structure. But we still need to alter the Grosvenor basis algorithm. But the first and really difficult step is to write down the correct data structure on which you will act. Yeah. To have an algorithm, you need a specification for the data structure, and this was actually before CAP impossible to think of. Yeah. We really need the full force of CAP to realize the equivariant symmetric algebra. Yeah. And then, of course, we have to think about what is the generalization of what we think of the necessity of a leading monomial and so on, and then it will be just leading. I don't know. Actually, we have a very good idea what it will be. It will be also a leading generalized monomial. Yeah, but then I have to define what is a leading generalized monomial and so on. Yeah, but then you run up into other problems that the whole thing is not even associative anymore. You know, only if you interpret it back in classical polynomials does it become associative again. Yeah, but what actually do you want to what actually do you want to test? You want to test ideal membership. Yeah, and you're not working with elements. So if you have a equivariant data structure for this ideal or this ideal, you can simply ask if this one is in that one or not. For this, you need concepts of syzygies. You actually you're doing the Grosvenor basis exactly like you're doing Gauss. Why are you doing Gauss in linear algebra 1? You're doing Gauss to solve systems, linear systems. And this means you want to solve inhomogeneous linear systems. This is called looking for the particular solution. If it's solvable, and this is translated in commutative algebra in the submodule or the ideal membership problem. It generalizes directly. And so this is called in category theory the lift problem. We have two arrows over the modules over this equivariant symmetric algebra, very simple arrows, and we want to see if there is a lift. Yeah, okay, and it will probably end up using a mixture of linear algebra and ordering, and there you will also have the flexibility of choosing different orders and so on. And the other thing is computing the homogeneous solution, and this is also computing syzygies. And you compute Grosvenor bases to be able to compute syzygies. You don't compute Grosvenor bases because you like Grosvenor bases. You compute Grosvenor bases for the membership problem and for computing syzygies. Yeah. So this is the goal. We want to decide lifts and compute syzygies. Yeah, and whatever algorithm we need, it will be just the intermediate step. Our goal is not the Grosvenor basis. Our goal is to be able to compute lifts, regardless how we can do it. If we can prove we have a lift, we have a lift.
Yeah.
Yeah.
Okay.
Okay. So let me show you the compiler. For the compiler, I came to this worksheet. So now you see the multi-layers of this. This is now a module, but actually it's multi-layered. So it have an active cell. So let's maybe go to the E. E is also a module. It have an active cell of E. So this is this one. It's a set of 6 relations for 7 generators of the HomAlg left module with ambient objects. So this is the generators. Yeah. This has an underlying cell, which is also an object in a category. This is the set of relations, but now without the generators. Yeah. And this as well has the so-called morphism datum. So let me think, what is this? Of object. Where am I now? Am I in fried? I'm in fried, so in fried, a relation morphism, not underlying morphism, I'm sorry. Under relation morphism. And inside here, I have the underlying matrix. And each of them, this is now the bottom data structure, which is again in HomAlg. Yeah, so the top level is managed by HomAlg, and the bottom level with this matrix is again managed by HomAlg, and in between is cap. And let me show you the categories. So the cap category of E, this is this here, the intrinsic category of the cap with a category with ambient objects. This is the one which is adding the intrinsicness. This is the one which is adding the generators. This is the one which is adding co-kernels to the additive category, and this is the ring, and this is the additive closure of the ring. And I showed you all 4. So now I go one layer by looking at the active cell. This guy has many cells, not just, this is the intrinsic guy. So it have the active cell, but it can also, it has definitely another cell at least. This is the one which is least possible. And probably this is still slightly bigger. No, so let's go to certain cell 1. Yeah, this was the horrible one. This is the one I started with. But all of them are in this category with ambient objects. And now inside this, I take the underlying cell. And now I get rid of the generators, and I'm in the additive closure of the category of rows. And for this, I go then, I peel it again and go then for the relation morphism of this. Then I'm in the row. This is now the category of matrices over Z. And there is nothing below. The only data structure below is the HomAlg matrix. Yeah? And what I showed you was something like generalized morphism by category, or something by 3 arrow object based, or 3 arrows based on the, I don't know what, the fried of the rows of the ring category, ring as category of, I don't know, Q, X, Y, Z, something like this. This is where I could do the computation, or actually even the, not this, but the Weil algebra of this. Something like that. And of course, if I want to do the computation, the computation starts here. It has to unpeel the first layer. I get down there and there and there and there and there, yeah? And this is the idea why we need the compiler. We need the compiler to do this unpeeling once and for all until we end up with the, so let me first of all share again, but now I share the browser. So let's go back.
So when you say a compiler, so what do you mean now?
I will tell you in a moment. So where's the compiler? Compiler for cap. So you click here. Yeah, so as you saw, we can have multiple layers. Yeah, and whenever you're doing a single algorithm, you have an input. Something I'm getting the internals out of the input. I'm doing an operation, and then I'm wrapping back. But of course, this algorithm that goes from here to here, of itself has to unwrap. Yeah. So this means that the algorithm that goes from here into here means that it again needs to unwrap its content and then do the algorithm for him to here, which also means that we have to unwrap. Yeah. And what we keep up doing all the time is that we unwrap, compute, wrap.
Exactly.
And then unwrap. And this is, of course, a constant overhead because it's not independent of the complexity of what's happening here. So this is the O of 1 complexity of the overhead. And what we're doing now is we're taking this here and turning this into that. Yeah. So we understand all the intermediate stuff and we don't unwrap in between.
Okay.
And
we don't wrap and unwrap in between.
Is this in some way a byproduct of the laziness to understand beforehand what computations should be done and at what level you will be for the next computation?
Yes, at least this is the goal. We will combine the compiler with lazy categories for CAP. At the moment, what the compiler does, it's a just-in-time compilation. So it follows until it reaches the matrices. And once it did it once for one object through the generic path, it knows what to do it, how to do it in general. But it doesn't do it for the branching. And what we are thinking about now is that we just write down linear algorithm. There is no branching whatsoever, and the entire logic will be moved to the compiler. The compiler will know about the branching at the bottom level. Actually, at each level. So the compiler will manage the logic for us. Yeah. And the compiler will also do the parallelization, because this is also another layer, which I also wanted inside the whole business. But actually also parallelization means that you understand the dependency graph of what you compute. And this is coming from the laziness. This is coming maybe from the logic that you don't compute too much. Yeah. And this is coming from this dependency. And then after you understand the dependency, you can even make another layer that takes the dependency, analyze it, and distributes the computation. Yeah. So you see? And this is really nice with CAP. And if you think about it a posteriori, then everything was actually clear. I mean, we have this programming language called category theory since 1945. The only thing is that people didn't really realize it is an abstract programming language for algebra. It was there with this very weird reputation of being abstract. But I never saw something more concrete than this language.
And so what I understand that this idea of following information and spreading it backward and forward, it's really embedded in the category language, but is there something similar in other language? Have you been inspired by something else than category?
No, I was inspired by GAP. GAP has only the forward. Actually, GAP has this idea of spreading knowledge, but the knowledge is just spread on one and the same object. So if a group knows that it is nilpotent, then the group should know that it's also soluble.
Okay.
But the knowledge cannot really travel. It cannot leave one object and go to another object. Although some people in GAP, because they also had this language facilities, they were thinking about extending GAP. And what we did in HomAlg, we extended GAP. GAP has so-called logical to-do lists. Whenever you create a kernel of a morphism, the kernel and the morphism are linked. And they know whenever I know something, I have to tell this guy, because he could use this information to do something else. And this is what we call the logical to-do lists. Of course, if we install these logical to-do lists are by default for every category. But now we have to, by default, disable them in the lowest categories because this is not where we want to do the logic. You know?
Okay.
And my current PhD student is now trying to reorganize CAP, that the stuff that is coming from my bad influence is now modularized. You know?
Yeah, it's impressive.
Yeah, very impressive. And so I have no more questions at this point. You answered a lot of questions. I don't know, Alban, if there is something.
I can discuss with Mohamed as much as I want. So yeah, but it's really impressive, and I think it's nice that to show this to mathematicians. I think this is the new generation. I think will use a computer and do maths together because they will be born with a computer in hands. You know.
Yeah.
And I think it's a chance for Mohamed to be the first real generation to do that. Because in one generation or two,
we really need people. So this stuff, you see, we're working on it constantly because it can only ripen when people start to apply it. I mean, you saw how many category constructors we had, yeah? But of course, a lot of them are not really optimized. They're working and probably maybe even bug-free, yeah? Maybe even bug-free because you saw how the procedures look like actually, and even the procedure in this category of functors, which is doing this parametrically for every limit. If you have a bug in this one, you will see it on the first limit that you apply it to. So even this abstract code, if you just go through one or two limits, you are 100% sure it will work for any other thing, even if the code is abstract. Let alone this other code, which is really readable. Take the arrowmorphism, the reverse arrow, pre-compose, take the fiber project into this. You can only have syntax errors in such a code. You cannot have anything else. Otherwise, CAP will tell you the stuff that I want now a commitment. CAP actually is better than GAP that knows that the stuff that will come out will be between a morphism between this object and that object. You know, so it's strongly typed, and if it doesn't come out, it will tell you, "I'm sorry, this is not the commitment." It's very much like Coq.
Yeah, exactly. It's really proof.
So more or less, the stuff is probably correct, but we need more. You know, we need people that start to use it and say this is slow, and then we figure out, oh, actually, we could add or replace this algorithm by that algorithm still categorically, and it will have a huge boosting effect on the overall performance and so on. And when I do application, I figure out I have to go into CAP and improve things. Yeah, things are working all in principle. I never get something wrong. I don't get the wrong answer. But I want to get something that I used to get with HomAlg. I want to get the speed that I used to get with HomAlg, you know? But of course, HomAlg was, again, just one area of application. You see, it was wide. I always claimed I had many applications, but still, it's limited. And this system can only grow if enough people start to use it and criticize it. And
have you tried to teach a category theory course based on CAP?
We are using it in our higher exercise classes. So when we are doing commutative algebra, then we let the students work with CAP. So so we have enough categorical input. So I'm now even teaching category theory in the first semester. Because I used to teach it in the third semester, but then I figured out actually the matrices, they form a category. Why don't I define it as such? Yeah, I now tell them a category, and a monoid is a category on one object, and then I can tell them what is an abelian category. So, and this is an abelian monoid where everything has a morphism, so it's actually an abelian groupoid, and you know, and I figured out that it works. they end up understanding it. And even for them, it's simpler. They now understand that all these notions are just special cases of categories with properties. Yeah. And now when we talk about the matrices, they're not. So ask any student in the third semester, what do the matrices build? He will not know. Of course, they're only partially composable. Yeah, but what are they? They are a wonderful category. The objects are the numbers, and the matrices are the morphisms. Yeah, and this category is equivalent to the category of free modules over the ring. But you even have something to tell them, that you have a computer model for something very nice. Yeah, and in the third semester, I will teach them Fried, that if you have such a thing over a ring and you want just to add, if you have weak kernels and you want to add co-kernels, you will end up having the category of finitely presented modules for free. And the Fried construction will just take an additive category. It will not take even a category of matrices.
So if you write your note in English, I would like to have them.
Yeah, we are actually doing this, but gradually. I now redid the complete linear algebra 1 from scratch to teach them a lot, but I'm not happy with it. I have to do it again. And the third time, it will be translating the stuff into English. Okay. And the idea is to write 6 courses using category theory, starting from linear algebra 1, linear algebra 2, linear algebra 3 will be Grobner bases, also using this language, and then algebra, and the fourth algebra will be the classical one, but at the end we will be able to compute Galois groups because we have Grobner bases in the third semester. So actually the idea is due to Cauchy, how to compute Grobner bases using Grobner bases, although he didn't know anything about Grobner bases. Yeah. And then in the 5th semester, commutative algebra, and then in the 6th semester, toric geometry. And all this, I mean, we have programs for all this using category theory, but it's long and it takes a lot of time. And this is education and not research. So,
well, in some sense, it is linked, and you will have great students at the end.
I hope so. I hope so. I hope so.
Okay. Yeah. Well, thank you very much.
Thank you
for this presentation, and okay, I hope we'll meet soon, maybe for real.
For real, yeah. And once you think about any question having to do with computer algebra, and you have a doubt, it could be approached using category theory or such an abstract formalism, then just let us know.
Okay. I will do it. I will do it. I will explain my problem, and you will categorize everything, and so
categorize everything.
Okay.
Okay. See
you. Bye. Thanks a lot.
Thanks.
You're welcome. Anytime. Bye.
You are currently the only person in this conference.